Welcome to the Springs Fundamental 103 class. My name is Gary Van Buren, your instructor for this session. This class is designed as an introductory class and will describe the different types of materials used in the production of springs. This program was developed by the SMI Technical Committee, and I hope you enjoy your session. The goal of the Spring Manufacturers Institute is to serve, support, and educate North American precision spring manufacturers in their pursuit of competitiveness in world markets. First, a few words about SMI. The Spring Manufacturers Institute was founded in 1933 by Associated Spring. The Spring Manufacturers Institute is an association of companies that manufacture springs and their associate suppliers. The members of SMI work together to meet the key issues of the industry worldwide: quality, materials, technology, and government regulations. SMI provides many services, including a quarterly magazine, Springs, a variety of technical publications, spring design software, industry data, seminars, meetings, safety and regulatory compliance information, and technical assistance. The Springs magazine is available in a digital format and can be searched for articles of interest. This class is part of the Fundamentals series. The organization of the presentation of materials in this training module follows the drop-down menu of the materials presented in the ASD7 software. Live ASD7 software demonstrations are provided for both existing customers and new prospects by Universal Technical Systems, free of charge via GoToMeeting. Presentations typically take about an hour. For more information, please contact Todd Pfeiffer. As you open the ASD7 software, you have options to select for spring type. For example, selecting a compression spring then leads you to the next window where you are able to select the material. In this window, material is shown in the top left. Select the drop-down box. These are the materials currently available in the ASD7 software. New materials can be added by individual users for their company's use. Materials are organized into the material families as shown: carbon steel wires, alloy steel wires, stainless steel wires, copper base alloy wires, nickel base alloy wires, cobalt base alloy wires, titanium alloy wires. For each of the SMI design courses, this 7-step process flow is used. The first 3 steps, define the problem, select spring configuration, and select materials, are critical to designing what the customer desires. Select stress levels and design to optimize are iterative steps that refine the design. Check design and specify are steps that lend themselves to finalizing the advanced product quality planning protocol. In this module, our focus is on material. This slide emphasizes that material selection is often dictated by experience or the particular application. With regards to selecting the stress level, it is important to know if the spring will operate in a static or dynamic condition. Is it prone to fatigue, or is it a safety critical application? With regard to material selection, engineering factors such as the operating environment, stress conditions, fatigue conditions. Is the spring being used in a static or dynamic condition? What do I mean by that? For a static condition, think of your hot water tank. The pressure relief valve will sit there for years and may only operate once in its lifetime. For a dynamic condition, think of your car's engine. You need the engine valve springs to cycle billions of times. There are also commercial factors to consider when selecting a material, such as cost and availability. What is a spring material? High-strength alloys ranging from medium and high carbon steels to beryllium copper depending on the need of the design. From cold worked, quench and tempered, to precipitation hardening processes. Ideally, they have high strength, a high elastic limit, and a low modulus. Materials are controlled by specifications. Below are some of the governing bodies responsible for the development and maintenance of standards. ASTM International is a voluntary international standards organization that develops and publishes consensus technical standards for a wide range of materials, products, systems, and services. IHS Market is your source for standards and specifications from the Deutsches Institut für Normung, also known as DIN. ISO is the International Organization for Standardization and publishes spring material standards. JSA is the Japanese Standards Association and publishes Japanese industrial standards for spring materials. Tables of cross-reference similar materials are included in the Encyclopedia of Spring Design, Volume Fundamentals of Spring Design. We will begin our discussion with carbon steel wires. Carbon steel spring wires. Types: music wire, hard drawn, oil tempered, and valve spring. Pros: they're the most economical. Cons: they rust rather easily. The applications are commercial and useful in ambient conditions. Note the max operating temperatures. Music wire 250 degrees, hard drawn 250 degrees, oil tempered 300 degrees, and valve spring 300 degrees. The next material of interest is alloy steel wires. Alloy steel spring wires. Types: chrome vanadium and chrome silicon. Pros: higher strength than carbon steel, improved fatigue life. Cons: plating is not recommended. Nominal increase over carbon steel in cost. Over the years, chrome silicon has become the most commonly used alloy wire and is the most readily available. Note: the max operating temperatures for chrome vanadium is 425 degrees and chrome silicon 475 degrees. Our third family of interest is stainless steel wire. Stainless steel 300 series, types 302 and 316. Pros: corrosion resistant alloy in normal atmosphere when passivated, and most economical of the stainless steel alloys. Cons: lower strength than the carbon steels. They come at a higher cost. Note that 302 and 316 have a max operating temperature of 500 degrees. Stainless steel, precipitation hardened. Type 17.7 pH. Pros: higher strength, after heat treat, and better long-term stability than 300 series. 17.7 pH is most popular spring alloy. Cons: they come at a much higher cost. Note the max operating temperature of 600 degrees Fahrenheit. Our next material family of interest is copper-based alloy wires. Copper-based alloy wires. Types: brass, phosphorus bronze, and beryllium copper. The pros: best conductivity of all the alloys. Cons: medium tensile strength and very high costs. Applications are normally electrical or electronic. And notice the temperature ranges for phos bronze is 200 degrees, beryllium copper is 400 degrees, and spring brass is 200 degrees. When we begin to think about high performance and exotic materials, nickel-based alloys are prime candidates. Nickel-based alloy wires. Types: Inconel 600, Inconel 718, Inconel X750, Niceband C, Monel 400, and Monel K500. Some alloys are heat resistant, and some alloys are seawater corrosion resistant. Cons: substantial cost increase over most other alloys. Applications: operating temperature range is from minus 300 degrees Fahrenheit to 1200 degrees Fahrenheit, and some alloys are good for cryogenic applications. Note the maximum operating temperatures. Inconel 600, 700 degrees. Inconel 718, 1200 degrees. Inconel X750, 1100 degrees. Niceband C, 200 degrees. Monel 400, 450 degrees. And Monel K500, 500 degrees. Next on the list is cobalt-based alloy wires. Cobalt-based alloy wires. Types: alloy and MP35N. Pros: non-magnetic. Cobalt, chromium, nickel, molybdenum alloys having unique combinations, very high strength, excellent corrosion resistance, and high fatigue strength. These alloys are highly resistant to sulfide stress corrosion cracking, and as a result are the alloy of choice in the most demanding sour well environments. In seawater, these alloys are virtually immune to crevice and stress corrosion and pitting at the highest levels. Cons: there's a substantial cost increase over most other alloys. The applications: springs, torsion bars, seals, medical devices and implants, and orthodontic wires. Operating temperatures range from cryogenic to 850 degrees Fahrenheit. Finally, titanium alloy wires. Titanium alloy wires. Types 38644, beta C. Compositions: 3% aluminum, 8% vanadium, 6% chromium, 4% molybdenum, and 4% zirconium. Balanced titanium. The pros: best strength to weight ratio among the metals. It's 40% lighter than steel and 60% heavier than aluminum. Good fatigue life when shot peened. Corrosion resistance, an exception being in a chlorine environment. Cons: some alloys can be difficult to fabricate and costly. Applications: aerospace, aircraft springs, race car springs, and in-body medical applications. Type 38644 has max operating temperature of 800 degrees Fahrenheit. The following slide contains material comparison charts. This chart is for carbon steel wires. Materials are shown by material type, quality level, specification, relative cost, tensile strength, maximum operating temperature, and atmospheric corrosion resistance. This chart is for alloy steel wires. Materials are shown by material type, quality level, specifications, relative cost, tensile strength, maximum operating temperature, and atmospheric corrosion resistance. This chart is for stainless steel wires and copper-based alloy wires. Materials are shown by material type, quality level, specification, relative cost, tensile strength, maximum operating temperature, atmospheric corrosion resistance. This chart is for nickel base, cobalt base, and titanium alloy wires. Materials are shown by material type, quality level, specifications, relative cost, tensile strength, maximum operating temperature, and atmospheric corrosion resistance. Thank you for your attention. I hope that you found this webinar to be of interest, and I hope to see you at a future SMI Basic or Advanced Training session. If you have any questions concerning this webinar, please contact the Spring Manufacturers Institute at www.smihq.org.